Hi everybody, today we are going to do some linear programming word problems. Okay, let's have a look at this first example. So this says a candy manufacturer wants to maximize the combined profit for two types of boxed chocolates. A box of chocolate covered creams yields a profit of $1.50 per box, and a box of chocolate covered nuts yields a profit of $2 per box. Market tests and available resources indicate the following constraints. So obviously, if there weren't any constraints, we would just say, hey, why not just make all of the product that makes more profit? But in this case, there are going to be constraints which might make it less profitable in the end of the day to produce the chocolate covered nuts. So let's have a look. It says the combined production level must not exceed 1,200 boxes per month. So we have one constraint here, and that's the combined production level. Then it says the demand for the chocolate-covered nuts is no more than half the demand for the creams. So you can see that the nuts actually just won't sell as much because the demand is just not there. Then it says the production level for the creams must be less than or equal to 600 boxes, and this is supposed to say plus 3 times the production level of the nuts. So we have another constraint there. So then they ask, what is the maximum monthly profit? So this is going to be the objective function that we're going to try to maximize. We're going to find one for profit. And then they ask, how many boxes of each type should you produce to yield that maximum profit? So we're going to use the question here to help us guide our variables. It says how many boxes of each type. So x and y are going to be the number of boxes. So we can say x equals the number of chocolate covered creams, and y will equal the number of boxes of chocolate covered nuts. So now we need to go back and we need to create our objective function because we want to see what we're trying to optimize. So our objective function is going to be for profit because they ask what is the maximum monthly profit, and we can create that. We can say P equals, when we know we get $1.50 profit in profit for each box of creams, and we know that we get $2 of profit for each box of chocolate covered nuts. So that's our objective function, but we have to also consider the constraints. So of course, we have two constraints right off the bat. It is not possible to produce negative numbers of boxes of anything, so we do need to include both of those as constraints. Then that first number one right here, it says the combined production level must not exceed 1,200 boxes per month. So that implies that x plus y must be less than or equal to 1,200. So when they say must not exceed, it means that it cannot go over 1,200, implying that it's a maximum. Then it says the demand for chocolate covered nuts, so I'm going to say y, is no more than, so we'll say is less than or equal to half the demand for chocolate covered cream. So y is less than or equal to 1/2 x. And then that last constraint says the production level for chocolate covered creams, so that will be x, must be less than or equal to 600 boxes plus 3 times the production level for chocolate covered nuts. So there we have it. This is a list of our constraints. So remember, to help us optimize our objective function, we're going to need to solve this system of constraints. And we're going to start by graphing them and finding our solution set. So the first two are really already taken care of if we just are working in quadrant 1. And then I need to make sure that it's very clear which line is going with which function. And I use color for this, but it's also really useful to maybe label them A, B, C, or however you want to do it. You just make sure that your work is organized. So for this first function, it says x plus y is 1,200. Remember, the best way to do these, I think, is to graph the intercepts. So if y is 0, x is 1,200. And if x is 0, y is 1200. And we can label those coordinates. Okay, for our next function, we have y equals 1/2 x. We have actually, it goes through the origin, and then it will just have a positive slope. And like I said, I don't typically do super accurate graphs for this because we can, just kind of estimate what the slope would be, and we'll still be able to tell where these lines are crossing. And then for this one, if you put this in slope-intercept form, you see it's y equals 1/3 x minus 200. So our y-intercept is somewhere way down at the bottom, which is outside of our quadrant. But we do have an x-intercept at 600. So it'd be right here. And then we have a slope that is positive, or it's 1/3. So it goes off in this direction. 600, 0. Okay, now we just need to figure out where to shade. So this first function would say y is less than, so it's below the red. This says y is less than, so below the blue. And this function, the y is on this side. So this actually reads y is greater than, so above the green, and of course it's above our x-axis. So our solution set would be in this region. So these are all of the possible values that work for our constraints. But of course, we don't want just something that works. We want something that works and maximizes our profit. So remember, this is always going to occur at one of the coordinates of your vertices of your bounded region. So we already know 2 of them, but we do need to find these other 2 coordinates. So this is why it's so important that your work is organized. When I look at my graph, I can clearly see that I need to solve the system between my red and my blue function. So I'm going to do that below. I'm going to use substitution here because I already see that y equals 1/2 x. But you can solve this in any way that you want. So we can say x plus 1/2 x equals 1200. I'm going to combine like terms and multiply everything by 2 just to clear my fractions. So we got x equals 800. And if you substitute that back into your blue equation, that means that y is 400. So this coordinate right here is 800, 400. So you might notice that our graph looks like it might not be making sense at this point, because if this point is 600 and this point is 800, it doesn't quite make sense. But really, that's just because our graph was such a rough sketch. Really, I guess this line should have been a little bit flatter according to our slope, which means it really would have crossed closer to here. But like I said, this shouldn't affect our final answer, and don't be concerned by that. As long as we've checked it algebraically, we should be okay. So now to find this coordinate, we're going to use solve the system of our red and green. So I'm going to use substitution again here. So we already know that x equals 600 plus 3y. So I'm going to substitute that into our red equation. And then we can solve. So y will equal 150. And if you substitute that back into our green equation, x will equal 1050. So that's going to be our remaining coordinate. Okay, so now we know all 4 coordinates of the vertices of our solution set. So those we are going to take and we're going to substitute into our objective function, allowing us to figure out which of these 4 coordinates will provide the biggest profit. And remember, the solution for optimization problems will always occur at one of the vertices. So if we check all 4, we should be good to go. So we're going to substitute into our profit function once again. And you do need to show all 4, even though you can probably guess that if you don't produce any products, you won't make any profit, but you still need to show that we've checked. So now let's substitute the next one. So that next coordinate will give us a profit of $2,000. Let's check our next coordinate. So that will give us a profit of $1,875. And our last coordinate at 600, 0 will give us a profit of $900. So these are the numbers on the right represent the profit. And since we were trying to maximize profit, that will occur at this value and at that solution point. So the maximum profit is $2,000, and we can achieve that by selling 800 boxes of, remember our X value represented the number of boxes of chocolate covered creams, and 400 boxes of chocolate covered nuts. And that's why it's so important for us to define our variables, because when we go to finally answer our question, we need to know what X and Y represent. So here's the entire problem written out. So you make sure you fully understand the different aspects. So there's creating the inequalities, there's graphing, there's solving algebraically, and then there's substituting. So there's a lot of different parts to these types of problems. Okay, let's try one more example together. So here we are told that the liquid portion of a daily diet is going to provide at least 300 calories, 36 units of vitamin A, and 90 units of vitamin C. So that's our daily minimum requirement from the liquid portion of our diet. So that's going to come from 2 dietary drinks, which we'll call drink X and drink Y, and it has to meet these daily requirements. Information about 1 cup of each drink is shown below. It says how many cups of dietary drink. So just the way it's worded, we can already use that to define our variables. So we can say X equals the number of cups of drink X, and let's call Y the cups of drink Y. Okay, so they say how many cups of each dietary drink must be consumed to satisfy the daily requirements at a minimum possible cost. So we don't just want to meet the requirements. We want to meet the requirements while optimizing our cost function. So our cost function is going to be our objective function, and we're going to try to find a minimum value. So we can use this information to help us find our cost function. So we can say C equals 0.72x, which is what it will cost for each cup of drink X, and then 0.90y. So this is the function we're going to try to optimize, but clearly there are some restraints, right? If there weren't any restraints, we would say, well, just drink X. But you can see that the different drinks provide different amounts of each vitamin, so there might be a different optimal value. So let's make all of our constraints. So I am going to start with our 2 obvious ones. X and Y must both be greater than or equal to 0, because it's not physically possible to consume negative cups of any drink. So now let's go through and see if we can use our daily minimum requirements and how much are provided to make our function. So if you need at least 300 calories a day, some of that's going to come from X and some will come from Y. So we can say 60X plus 60Y. And since it's a daily minimum requirement, it must be greater than or equal to 300. So it's okay to be at 300, although that's a little bit close to being too low. And it's definitely okay to be more, but it's definitely not okay to be less. It's a daily minimum requirement. And I know that because it says at least. Now it says we need 36 units of vitamin A. Some of that will come from drink X. So 12 units would come from X. 6 units would come from each cup of Y, and that must be at least 36 units, so greater than or equal to. And last, we need 90 units of vitamin C. Some comes from X, some comes from Y. So 10X plus 30Y must be greater than or equal to 90, the daily minimum requirement. So here's our constraints. So we're going to solve this system to figure out the possible optimal values. So this takes care of the first 2. We're just going to focus in quadrant 1. And once again, I'm going to graph by color, red, blue, and green. So for our red function, we can mark our intercept. So it will be at 0, 5. And actually, I'm just going to do this. Oops. I'm going to give us a little bit more of an accurate graph here. So we have one at 0, 5 and 5, 0. And then for our blue function, if x is 0, y is going to be 6. And if y is 0, x is going to be 3. And then for our last one, if x is 0, y is 3. And if y is 0, x is 9. So that actually goes a little bit off our graph somewhere over here. So let's assume that this point is at 9, 0, even if it's not quite drawn to scale. Now if I look at my graphs, I can see that this one says y is greater than, y is greater than, y is greater than. So our solution will be at the overlap and shading of everything above our lines. So it's actually going to be in this region. So we can see in this case, we do have an unbounded region. So we know that with unbounded regions, sometimes you don't have a optimal solution. So in this case, we actually would not have a maximum value, but that's okay because we are actually trying to find a minimum possible cost. So even though this is unbounded, we can still find a solution for what we're trying to find. So one of our coordinates is going to be at 9, 0. That's one we will check. We also have this coordinate at 0, 6. But we still need to find the coordinates of those two vertices because it's possible that those would represent where our minimum cost would be. So I can clearly see here that I need to solve the solution or the system of my blue and red equations, or however you labeled them. So I'm going to do that using substitution. I'm going to take my red equation and solve for x. And then I'm going to substitute that into the blue equation. But like I said, you can solve this system however you want. If you would rather use elimination, that is completely fine. So we can say 24 equals 6y, so y will equal 4. Oops, sorry about that. Which means that x will equal 1. And that actually does match up really nicely with what our graph looks like. Okay, and then for this coordinate, I can see that we need to solve the system of my red and green equations. So once again, I'll solve using substitution. We already know that x is 5 minus y, and I can substitute that into our green equation. So we can say 20y equals 40, so y equals 2. Which means x equals 3. And that looks just about perfect for our graph. Okay, so now we have our 4 coordinates to try. So we're going to substitute all 4 of those. Here's our 4th one up here into our objective function. So you do need to know that all 4 have been checked. So let's start plugging those in. So we could say 0.72 times 0 plus 0.9 times 6, and that will give us a cost of $5.40. Let's plug in our next coordinate at 1, 4, giving us a cost of $4.32. Now we're going to test the coordinate 3, 2, giving us a cost of $3.96. And then let's check our last coordinate at 9, 0. And that gives us $6.48 of cost. So remember, our goal was to minimize the possible cost. So I can see that our minimum possible cost is $3.96. And we can achieve that minimum cost by consuming 3 cups of drink X and 2 cups of drink Y. And remember, we had defined our variables here, so it's very clear how we're going to write our final answers. Okay, so have you guys pause the video and give this problem a try. Okay, let's have a look here. So the first thing I'd like you to check is your objective function, which is for cost, and you have 5 constraints. From there, you should check your graphs and check the coordinates. So you had to find these 2 coordinates. They should be at 1, 4, and 3, 2. Here's how I solved them. And then once you have your 4 coordinates, you need to substitute all 4 into your cost function. And you're looking for the minimum cost, which will be $105. And you can achieve that by using 3 bottles of nutrient X and 2 bottles of nutrient Y. All right, that is all for today. Thank you for watching.